I welcome you to this lecture on econometric methods. Today's discussion would be on the topic of lagged variables. In view of the nature of economic theory, any realistic formulation of economic models should involve some lagged variables among the set of explanatory variables. Lagged variables are on way of taking into account the length of time in the adjustment process of economic behavior and perhaps the most efficient way of rendering them dynamic. So, in economics, the dependence of a variable y on another variable is rarely instantaneous. Very often, this y responds to x with a particular lapse of time. This lapse of time is called as lags. Let's take an example of a consumption function, as you can see over here. Your consumption is a function of income at the same period yt, and we are also taking a lagged income. Means today's consumption, this month's consumption doesn't depend on the income of this month itself. It obviously depends upon what I have been earning in the last month, and not only last but also last few months. So this lag term incorporation is being done over there. Apart from that, we have this wealth and all, that's fine. But our main emphasis in today's lecture is on this particular component, that is the consumption of today. It depends upon what you have, what was your income in previous years also. Again, another example over here is of this investment function. See, investment is a function of output. Today's investment is a function of today's output, but along with that, it is also a function of past output. Plus, you have this profit, you have this capital stock, rate of interest, agreed. But what we should incorporate over here is that past output also has an impact on the investment for today. There are numerous reasons for this lag, like we can say psychological reasons. See, consumer behavior is based on the force of habit or inertia. People do not change their consumption habits immediately following if there is a price rise or there is an increase or decrease in income. This may be due to the process of change involved in some immediate disutility. Therefore, change in consumption habit is a slow process depending on whether the change in income is, say, permanent or it is transitory. Now, it could be the technological lag. Like say, production of a commodity requires time, therefore, supply of a particular commodity depending on its production process and the lagged prices of inputs. Say, the price of capital relative to labor, reduces. Now, substitution of capital for labor becomes feasible for the producers. Moreover, addition of capital to the production process takes time. If the fall in price of labor is expected to be temporary, producers may not substitute capital for labor, but they rather expect that after this temporary drop in the price of capital may increase beyond the previous level. Thus, you can say that the current output depends on the past investment. Then there could be, say, institutional reasons for this lag. Say, contractual obligations may prevent firms from switching from one source of labor or from one raw material to other. Similar, say, employers often give the employee of taking the choice of health insurance. But once you have taken a health insurance, you will not be able to switch it in that very year. At least you are stuck with it for a year. So, although this is done for administrative convenience, the employee is locked for over a year. So, these could, not only this, but there are other reasons also because of which this lag needs to be incorporated into analysis. This example over here this is, see, economic theory, whenever recognizes the importance of time lags, never suggests the precise number of lags that should be included in the function. Rather, the pattern of lag is explored and determined from the available sample observations. The researcher experiments with models including different lag patterns, say geometric or polynomial or arbitrary, and chooses among them the one that gives the most satisfactory fit. We will discuss an example based on this. Like, see, the same thing, this was an example, it was a study done by Alt and Tinbergen. He applied the OLS sequentially and he regressed this fuel oil consumption Y on new orders based on quarterly data. For the period, it was 1930 to 1939. Now, what happened? Once he has taken XT, fine, 0.17. So, what he is taking? New orders. Now, next time also, it's fine. He has incorporated one period of lag. So, it is y hat t is equal to, first it was 8.37 plus 0.171 xt. Next time it is y hat is equal to 8.27 plus 0.111 xt plus 0.064 xt minus 1. The third time, up till here it's fine. But the same thing which was positive, having a positive sign earlier, with another inclusion of another lag, the sign changed. So, see, Alt in his study, he chose the second regression as the best one because the last two equation, the sign of xt minus 2. Now, here also the sign problem. And it was negative, which may be difficult to interpret or not feasible. So, what is the basic is we can increase on, we can incorporate, but how many to incorporate? How many variables should I take? How many lag terms should I take? This is what what we will be discussing in this unit also. See, we have distributed lag models wherein xt, a lag of xt minus 1, again a lag of xt minus 2, and you can keep on incorporating it. There will be another type of equation over here which is an autoregressive, whether this yt is present as a lagged, the dependent variable is present as an explanatory variable. Now see, now the estimation which we had done, now there are certain drawbacks. There is no a priori guide as to what is the maximum length of the lag. As one estimates successive lags, there are fewer degrees of freedom left, making statistical inference somewhat shaky. Economists are not usually that lucky to have a long series of data so that they can go on estimating numerous lags. The more lags you incorporate, the more degrees of freedom you are losing. So, more importantly, in economic time series data, successive lag values tend to be highly correlated. Again, so then the problem of multicollinearity also arises. So, no priori guide, fewer degrees of freedom, and the issue of multicollinearity happens when we try to estimate through the ad hoc estimation which we had seen in the ad hoc estimation means I refer to this type of case. So, now it can be finite. So, a finite one is where the last term is defined, and infinite where you don't know what is going to be the last term, it is going to continue and continue. So, you can classify it into finite, one which has a defined lag length, or it can be infinite. So, we come back to our discussion on distributed lag models and lag variable model. So, distributed lag models are which include lagged values of the among the set of explanatory variables. They are called distributed lag models because the influence of the explanatory variables on the dependent variable is distributed over the past values of x. Lagged values of the variables are important, explanatory variables in most economic relationship, because an economic behavior in any one period is to a great extent determined from the past behavior or past experience in those things. So when we are applying OLS, we are, because of the lack of data, or we can say the lack of the degrees of freedom, we face issues, and face issues because of multicollinearity. Now there are many procedures to estimate these models, but there is advantage and disadvantage of each one of them. But the basic purpose of all the upcoming models which we will be studying is that we will be concentrating on how to meaningfully reduce the number of parameters to be estimated. Here also your error terms assumptions are the same. Expected value of ut is 0, expected value of ut minus 1 is 0, and the variance is constant, our old classical linear regression assumptions. So now we move on to estimation. See, our concern is mainly to find ways for economizing the degrees of freedom, that is to reduce meaningfully the number of parameters to be directly estimated from the given sample. The simplest method is to construct a new variable W from a linear combination of the lagged x's, the independent variables, assigning arbitrary numerical as weights for the individual lagged variables. There are many versions: declining lag scheme, rectangular, inverted. We will be just going quickly have a look at these. Now here it is an example where we are assuming that S are 4 terms, 1, 2, 3 and 4. So we have taken a lag of 4. You can see that the lag is declining. It is assumed that the weights are declining. That is, the more recent values of x is having a greater influence on y than the previous older values or the remote values of x. So here we have, now we can see that, the weights 1 by 3, 1 by 6, 1 by 6, 1 by 6, 1 by 8. So it is reducing, and that is why you have this picture where it is your declining, geometrically declining weight you are seeing over there. Then the rectangular lag scheme. In this lag scheme, all the lagged values are given equal weights. That is, it is assumed that each past value of x is having the same influence on y. So 1 by 3, 1 by 3, 1 by 3, 1 by 3, 1 by 3. Weighted for xt minus 1, xt minus 2, xt minus 3 and xt minus 4. So, and the die picture you can see, you can denote it like this. Then you have this inverted V pattern. Here it is assumed that the weights are initially increasing, then subsequently declining. 1.10, then it becomes 1.4, then it becomes again increases, again it becomes 1.5, 1.7 and 1.9, inverted U-shaped. So these are some of the patterns, possible patterns. In many applications, economic consideration may suggest that what is the most probable pattern of lag structure. For example, in a consumption function, the declining weights of the past levels of income seem more plausible, while in an investment function where the lagged x are past capital appropriations, it may be more reasonable to assume a inverted V scheme. In general, the method of arbitrary weights is an extremely arbitrary method of dealing with the lags. The researcher specifies not only the general form of the weights, declining, rectangular or inverted, but he also assigns lagged values to the weights of the lagged variables, like as we can see over here. So the choice among these alternatives, The choice amongst these alternative model is basically based on the statistical criteria, that is the goodness of fit and measured by R square and the size of the standard error of estimate. Sometimes rationalization of the choice is attempted on a priori economic consideration as well. So what we have, so having we have, see, this C1 W1T alpha 0 alpha W1T, and we have finally like this. You can continue. W1T is equal to 1 by 6 xt1 xt minus 1 plus 1 by 5 xt minus 2 plus 1 by 5 xt minus 3 plus 1 by 8 xt minus 4 and so on. So these constitute your probable W. In order to further explain this process, let's take an study by Deleuze, study which is famous by the name of Deleuze study of investment. It's a good example of arbitrary weight lag scheme provided by Deleuze based on, say, quarterly data. He experimented with the following three types of distributed lag function. This is 1, then you have this 2, then you have 2 and 3. So the first one, here the value of this lambda is more than 0 and less than 1. This is the standard distributive lag function with declining weights. With the declining weights, the weights are geometrically declining. This form was also suggested by Koek. We will see Koek in detail. Then we move on to the next one. Next one, this is a lag scheme with constant weights. Here it is lambda, then lambda square, then lambda cube, then lambda, and then lambda raised to the power s for when it is extending up till s. But in here, in the second one, it is w, 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 and it's all constant. Then this is the third one. This is a function with an inverted V lag pattern where the weights initially increase and then fall. In particular, Deleuze assumed that for a total lag of S periods, the first half the weights are proportional to the increasing series and the other half of the weights are proportional to the declining series. Deleuze, after numerous experimentation with various lag periods, concluded that the best fit was the one obtained by a function of the third type, that is the inverted V, and with a 12-quarter period lag, that is S is equal to 12. His preferred function is on the basis of, and he decided this on the basis of, obviously, the coefficient of determination, that is R square. So these are what we can understand as the ad hoc. We go on experimenting, we go on increasing the lags, check the R square, see whether it is significant or not, and things like this. Then we come to an ultimate decision. Now we move on to a few of the very important schemes or formulas or methods which are used in commonly used in lag variables, to study lag variables. The first one is Allman's distributed lag scheme. Now, in Allman's distributed lag schemes, we are simply first assuming a simple structure: beta naught xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 and continuing. And your ut is your error term, and we assume that it is satisfying all the classical linear regression assumptions. Now, these b's can be approximated by another function z. So, b is a function of z, where function of z is a polynomial in z of r degree, meaning thereby, so fz is equal to a naught plus a1z plus a2z square plus a3z cube, continuing up till ar z raised to the power r. So the degree of polynomial, that is r, it has to be assumed. For our purposes, we keep it small. Say we keep it up till 3. So we assume that r is equal to 3. So we have, this is the last term, a naught a1z a2z square plus a3z cube. Now let us have a look at it. So what we are doing, we We can approximate the b's by substituting the values of z starting from 0 and going on, meaning thereby when z is equal to 0, this is also 0, this is also 0, this is also 0, what is left is only this. So, what is left is A0. Now, when z is equal to 1, so here also 1, here also 1, here also 1, here also 1. So, we have A0 plus A1 plus A2 plus A3, that all the z cube and z squared, they become 0. Next time when a function is 2, so okay, this A0 comes as it is. Now here A2 A1, 2 raised to the power 2, for in place of z you simply write 2. So 2 square. In place when you are z3, in place of this you write 3, and you in here incorporate. Next time when beta is 3 is a function of 3, so what you do, 3a1, then 3 square a2, then 3 cube a3. This is called as the B system. This together is called as the B system. We are doing nothing. We have to assume that we will take 3 R's, 1, 2 and 3. So when it is 0, everything, because z becomes 0, 0, 0. So the last 3 terms disappear. Only what is left is a0. Next time in place of z you just write 1. For this one, in place of z you just write 2. In place of 3, in B3, in place of z you just write 3. So you get this. So like when you write 3, z3 and then a3, it is as it is coming. So this is called as the B system. Now the same thing, what was written over here, it is given in the side, not just for the sake of, so that we don't have to flip back to our thing. Now we substitute the values of b in the original equation. What is our original equation? We started with this. Now in place of b0, what was b0? A0. So I wrote over here. In place of b1, what was b1? A0 plus a1 plus a2 plus a3. So this I write, and then xt minus 1 is coming out. Next time b2, what is b2? We have seen over here a0 plus 2a1 2 plus 2 square a2 plus 2 3. This we write over here, and from here you write x2 minus t. So what we have done, now the a's are in the bracket and x's are outside the bracket. I hope it's clear. We are simply substituting. We have just in our previous slide, we have done the calculation for B1, B2 and B3. Now B1 and B2 and B3, they are present over here. So we are just putting the values of B1, B2, B3 and likewise. So we get this, the next system. Now then just the previous slide is written over here for your understanding. If you remember, this is the entire B1 xt minus 1, this is B2 xt minus 2. Now what we are going to do, see, A0 has xt, but apart from that, see, herein you have xt, so xt is there, xt minus 1 is there, xt minus 2 is there, and these are all, xt also has a0, xt minus 1 also has a0, xt minus 2 also has a0. So this is, now the a0s are written over here. Next time for a1, see, for a1 there is nothing over here, but a1 is present here. I write, so this is xt minus 1, I write xt minus 1. A1 is present over here and it is 2a1, so I write over here 2xt minus 2. Next time a1 is present over here also, 3a1, so I write 3xt minus 3, and a1 I write outside the bracket. I repeat again, for this, say for the term a2, a2 is not present over here, nothing to be done over here, but a2 is present over here. So a2 for xt minus 1, 2 square a2, 2 square xt minus 2. then 3 square A2, 3 square xt minus 3, all these present, and this is multiplied by A3. So we can take A0 as common, then we take A1 as common, then we take A1, A2, A3 as common, and so likewise we can write this system of equation in this format. So now what we do, the thing which we have this, what we are doing, we are simply denoting this, the first one as W1, the second one as W2, then W3 and W4. Then we incorporate it in, instead of this we write that. So what we have, yt is equal to xt plus xt minus 1 xt minus 2 a0, then xt minus 1 plus 2 xt minus 2 plus 3 xt minus 3 a1, then xt minus 1 plus 2 square xt minus 2 plus 3 cube 3 square xt minus 3 a2. So now in place of this we simply write w1, w2, w3 and likewise. So what we are doing, we are just defining this. This is what you called as W0, this one is W1, this is W2, this is W3 and likewise. So now how many terms we are having? 1, 2, 3 and 4. This is the error term, we at the moment leave it. So we are having 4 terms only. Initially we did not knew how many lags we are going to take. But now what we have got only 4 terms. Now we can apply OLS and obtain A0 hat, A1 hat, A2 hat and A3 hat. So now what we can have, so this is the same thing now you can do, you have only 4 terms we can got for A1 hat and A2 hat. So in Allman's distributed lag scheme, earlier we were not sure how many variables should we incorporate. We have come on, we are writing this equation, our original equation. This here there is xt minus 1, xt minus 2 and this is extending. This can be written in this format with only 4 terms. So the actual parameters can be estimated indirectly, and now there is no problem of multicollinearity. And initially what was the case? If you have a look at this equation, xt minus 1, xt minus 1, xt minus 2, GDP of today, GDP of 2022, GDP of 2021, GDP of 2020, obviously there will be a type of relationship between these. Or if there are 3 variables, we are taking a lag of each one of them, obviously there is much chance of having a problem of multicollinearity. But now once we have transformed this and we are estimating this, now this problem of this multicollinearity is not there, because now we are writing in terms of A0, A1 and here this is there, next time this is the W1 and W2. So this is one of the most commonly used model, that is the Allman's distributed lag scheme to deal with the lagged values. I hope the lecture is clear to you. Thank you for the moment.